Solving projectile problems using vectors. Projectiles using vectors in component ij form or column vector form. This ball is projected with an initial velocity of 2i plus 10j meters per second. We could give that same velocity using column vector form. The velocity at this point has a horizontal component of 2i meters per second. It has not changed. And it's still not changed, and you'll notice it's the same right throughout. The vertical velocity component was 10j meters per second. It's now changed, and again it's reducing until it's 0 at maximum height, and now it's negative as the ball comes down. This is the initial velocity vector. The magnitude of this velocity is given by Pythagoras' theorem, which is 10.2 meters per second. So we could say that initially this ball was projected at a speed of 10.2 meters per second. We can easily work out the angle theta using basic trigonometry. Tan theta is the opposite over the adjacent, so 10 over 2. We solve this, so theta is 78.7 degrees above the horizontal. So the velocity of the ball can be given like this, where you have the magnitude and the direction of the arrow with the angle. Together these give the vector magnitude plus direction. Displacement vectors versus position vectors. This ball has a starting position at A. Displacement is always measured from the starting position, so displacement vectors here will be measured from point A. So initially the displacement vector S is 0i plus 0j. We could write that using units as well. A is 5 meters above the origin, vertically above. Position vectors are always referenced from the origin, so from this point. A is 5 meters above the origin, so we can use the vector 5j, representing 5 meters vertically up. So the position vector of the ball relative to the origin is 5j meters. At this point, the displacement vector of the ball, so relative to where it started, is 3i plus 8j meters. We want to work out the position vector for the ball at this point. The position vector of the ball here is a combination of the initial position of the ball, which was 5j meters, plus the displacement from point A. At this point, the displacement vector for the ball is 6i plus 12j meters. Again, to work out the position vector, we have to add on the initial position, 5j. And again here, we've got the displacement vector again, so this is the position of the ball relative to point A, 14i minus 5j meters. And again, the position vector will be your displacement vector plus the initial vector of the ball, which was 5j meters. Here we have a horizontal plane and an origin. A ball starts from the origin. In this case, the position vector and displacement vectors are exactly the same. We can convert between component ij form vectors to column vectors. So as an example, if we have a position vector like this, we can write that using column vectors. So 5j is 0, 5, 6i plus 12j is 6, 12. We can simplify, so the 0 plus the 6 is 6, 5 plus 12 is 17, and in the component ij form, if we add up all of the I components, we've only got this one, 6i. J components, we've got 5j plus 12j, 17j. And these are the same. we can use SUVAT formulae in their vector forms. So here, velocity, initial velocity, acceleration are all vectors. So here they are in their vector form. T is a scalar. Same again, we've got the vector form here, so we're going to use these with component ij vectors and column vectors to solve problems. And again, this one doesn't lead to anything useful because we've got v squared and u squared. We're not going to square our vectors on this side, so we ignore this one. And the last one. Remember to underline these letters. These are all vectors. T is not a vector, it's scalar quantity. When solving projectile problems using vectors, we always take these two directions as positive, because these are the positive directions for the component ij unit vectors. The acceleration vector in our SUVAT formulae will have a magnitude of 9.8 meters per second squared. Gravity only acts in the vertical direction. Gravity acts downwards, but this arrow is pointing upwards, so we need a minus in front. So this is our acceleration vector. I can replace the 9.8 with g.